Hello, this is Bhavik. I'm going to attempt solving this first question. So here we have two players called Lata and Raj. Let me just Lata and Raj. Let's just denote that with L and R. And these we have 9 tokens. These players take turns alternatively removing these tokens. They can either remove a single token or a pair of tokens connected by an edge in each of their turns. And the player that removes a token or a pair of tokens at the end wins the game. And we are supposed to analyze if there's a specific player who will always win a game or the strategies that players should employ playing this game. First, we need to note that there are chances that both of these players cooperate to make a specific player win. And here we're going to assume that they'll not do that. They'll act rationally and try to make themselves win. Also, here there's symmetry. There's rotational symmetry as well as mirror symmetry. So I can take an axis like this, flip it, and then get the same thing. So instead of analyzing all configurations, it would be best to just analyze cases that are equivalent up to isomorphism. So Lata starts the game. Let's say she plays this edge, and that would be just as equivalent as Lata playing this edge, meaning removing these two tokens. Okay. So Lata can either play an edge, remove tokens, or she can take away a specific token. We can form a tree, uh, mapping all these possibilities in a tree. Okay, I'm also going to give some notation because here we need to analyze the configurations and not the specific edges. Let me just number them anyways. If we go about analyzing each specific way that the game can go on, then this tree would be really huge. Instead, we can only care about finding a representative uh, game play that these players would play, and each of these would represent the other configurations, and that's because of symmetry. So L is playing this 1-6 edge, and that's just as equivalent as playing 2-7. Let's say next R is going to play 7-3. Now this case is equivalent to L playing 9-5 and R playing 6-2 because that's just the rotator version of this. So yeah, that's the reason we are only cared about finding representative configurations and not all specific configurations. Let me also give a convention. Like I'm going to denote, classify these tokens into different categories. I'm going to represent circle of for the tokens that have been removed. So 1 and 6. I'm going to use square for the neighbors of these circles. So 2 and 5. Next, I'm going to use triangles of neighbors of these squares. And the reason I'm doing this is to better analyze the situations so that I can generalize it better instead of dealing with each and every specific case. And let's say the neighbors of these triangles are diamonds. And there's one left out vertex. Let's just name it stars. Okay. So after L plays an edge, it can either play this or this, but let's say it plays an edge. We can do this classification just after it plays. So let's say it plays 2-7, then these two become circles, and then the pattern follows. Now player R can either play 3-8 or 4-8, and these two are equivalent, as you can see. 3-8 is not the same as playing 5 and 9, and that's apparent when you look at what categories these tokens are from. So yeah, let's say R takes the decision of playing 3-8, which is an edge between diamond and star. And let's represent that with red color, clear R. Okay, now what happens? These two become circles. Let me do that. Let's first erase. Okay, so this node in the tree represents all those gameplays where L plays an edge, meaning removing two tokens, and then R plays an edge between diamond and star. Okay, now let's see what happens. How many square vertices do we have? 1, 2, 3, and 4. So here we have 4 squares. That's an outcome of playing this 4 squares. And now whose turn is it? It's L's turn again. So let's say L plays another edge. And now let's not just draw the graph, we can just analyze it here itself. Let's say L plays 2-7. Then there's a way for R to win. How if R plays 9, L plays 5, and then R plays 2. Similarly with other edges as well. Let's say it plays 5 9. So R can play 2, L will play 7, and then R will play 4. Again, R wins. And what are the edge? Yeah. And 9 and 4. The same thing happens. If L plays 9 and 4, R still has a way to win. So yeah, if L plays with an edge now, after these two moves, R will win. And let's say if L plays a vertex, what will happen? So we have 1, 2, 3, 4, 5, 5 vertices left. And there's symmetry here as well. Let's say uh, L plays with 9, then R can play 7 2, which would force L to play 4, and then R will play 5 to win. So yeah, still L loses if it plays 9, and 7 and 2 are symmetric. Let's say L plays 2, then R will play in 5 9, L will play 4, and then R will play 7 to win. Similarly with 7, because they're symmetric, and 4 and 5 are also symmetric. Let's say L plays 4, then R can play 5 9, L will play 2. No, L can play 2 7, so L will win. But okay, let's say L plays 4, then I can just play 5 instead of 5 9, and L can play 2, making R play 9. Okay, wait. I think there's a way for L to win here. Now, if L plays 4, then it will win 4 or 5. Let's say L plays 4 and then R plays this edge. L can end up with this edge and win. L plays 4 and then let's say R plays anything. Let's say L plays 2. L can play 7. R will have to play the 5 or 9. And then L is left with the last token. So, yeah, what do we analyze? If this one would be a triangle, right? Yeah. If L plays triangle, then R would win. Triangle or these two. But there is a way for L to win. And how do I describe these two vertices? Okay, so these are vertices which have circle and triangle as their neighbors. Vertices with circle and triangle as their neighbors. Yeah, if L plays this, then L would win. In all other cases, R would win. We also analyzed all the edges. Any edge that it takes, R would win. Similarly, we can go back and analyze in step 2 where R would play some other edge. Instead of diamond and star, it can play an edge like 4 and 9, square and 9. And if you calculate, you would notice that it would lead to 3 squares instead of 4. And we can keep doing this basically as the game plays out, and you can exhaust till the end and analyze who would win. And based on these, each player would take a decision whether they want to uh, reach a certain stage. So let's say in all these branches, R is winning. Then L would choose not to take this edge, and it will instead try to go to the other option. So this is a forward approach. There's also a backward approach that we can do. Okay, I don't think we need numbering. Yeah, so the backward approach would be to say uh, that a person won. Let's say W is the player. We are naming the person based on who won. So let's say player W is the person who won, and player L is the person who lost. And we can do a backward reasoning as well. So let's say all these tokens have been removed, and there's only one token left. Player W is going to choose this and then win. Then let's try to use a backward reasoning for this. Now, what would player L's move be? Would it be this vertex? It would definitely not be these two vertices. Why? Because if we were left with these two open tokens, then L would just choose this edge and then win. So what that means is if W is winning with a vertex, so here also we can draw a tree. W wins, and there's another. Yeah. So let's analyze what the previous step could have been. Yeah. So the previous step, there's no possibility of L removing this or this. Why? Because if this vertex and this vertex were open, L could have just chosen this whole edge and win for himself. So yeah, if W is winning by removing this token, there's no way for L choosing a neighboring token, and this wouldn't happen. This won't happen. Let's think about other vertices. Could L choose this and make it win? Yeah, that's possible. Because if these two were open, L can either remove this and letting W win, or L can remove this, letting W win here. So yeah, one possible previous move could be this is one approach. One thing that could have happened. Could L remove an edge that's not touching this, and edge something like this? No, this is also not possible because let's say these three tokens were open when it's L's turn to play, and L wouldn't remove this, letting W win. L could have just removed this, letting W play one of these, and then the last move would be L's. So yeah, another thing you can say. So this is also not possible because these are irrational players. So yeah, let's say it's L's turn to play, and then these three tokens are open. L wouldn't play this edge, letting W win. L can play this, making W play this, and then L can play this again. Or L can play this, letting W play this, letting L play the last move. Yeah. So by this, what we can say is if the winning player wins by removing a single token at the end, the only possible way would be for the losing player choosing a non-neighboring token. These two things are not possible. Similarly, we can analyze this part as well. The winning player winning by removing a pair. Now let's say player W, let's say all these other tokens are removed at the end, and then only these two tokens are left. And player W plays this to win. Now we can analyze what happens on this side as well. So is there a possibility for player L to be playing a neighboring vertex? Could player L be playing this, letting W win? Because if L played this, W would just win. But let's say these three were open, L could have just played this, forcing W to play one of these, and then L would win. So yeah, there's no possible way that the previous move would be for L to be playing this, which is a neighboring vertex to the edge. So this is also not possible because L is also rational. It wouldn't choose this. It would instead go for this, forcing W to lose. So if W is winning by playing this edge, that means that this cannot happen. L wouldn't have played this. And what about non-neighboring vertices? Let's say this is open, these three were open, like L's turn. L could have gone for one of these, forcing W to play one of these two, and then L would win. So another thing is not possible, which is L playing a non-neighboring vertex. This also wouldn't happen. Okay. Could L's move be playing a non-touching edge, such as this? Could this be L's move? Yeah, because let's say four of these tokens were open. L could have played this, letting W win here, or L could have played this, letting W win here. And yeah, if W is winning by removing a pair, then that only means that in the previous turn, L plays a non-touching edge. This is a forward approach and this is a backward approach, where we are saying W wins by removing a token, and the only possible way is for this to happen. The previous player chooses a neighboring token. And if W is winning by removing a pair, that only means that the previous player plays a non-touching edge. And we can keep expanding this tree, this backward reasoning tree, to infer more rules and then check who will win at the end. Because at the end of the day, we want whether W is L or W is R. And this is a forward reasoning tree where we can analyze each of the cases and see how each player would strategize.